As you said, I'm Justin. I'm the head of infrastructure at Antithesis. In case you don't know what Antithesis is, we're a startup based in Northern Virginia. We're a software testing as a service company. Other companies basically give us their software and we put it in an isolated, deterministic hypervisor that allows us to kind of explore the multiverse of different possible executions. We basically just kind of like hit it with a bunch of rocks and sticks and see where things break. And then the customers have the ability to kind of rewind to the moment in time in that particular branch where their software broke and see what was going on, maybe rewind a second or two or 10 or 60 and see what was happening in the lead up to those failures. So it's a pretty powerful tool for being able to understand and debug complex distributed systems. Who am I? My formal background is actually in data center efficiency. My research was on figuring out how to balance utilization and power and cooling and networking in a data center and then tie that all back to money and how you make kinds of trade-offs. Out of grad school, I went to Google, and you can probably take a guess at the kind of stuff that I worked on there initially. Eventually, I actually transferred over to the civics team and ultimately was responsible for all of the civics data that went into Alphabet, just like basic information like where to vote, election results. You can see like some of the features that you might have seen on Google search before. I was there until about 2013. I got hit kind of like in that first round of layoffs, at which point I did the only thing that has ever impressed my kids, which is my LinkedIn post about getting laid off went viral. Nothing else. I'm like, I've met Obama, and they're like, yeah. I've met the owner of the Dallas Mavericks. I'm like, yeah. I got laid off, and 15 million people saw it. Wow, really? Anyway, a few months after that, I joined Antithesis, and I've been there ever since. I also have a side hobby doing sports analytics, mostly college football and Formula One. I think I generally just kind of like things that have a lot of risk and go very quickly. So yeah, ask me about Formula One. Okay, so for this talk itself, I'm going to kind of walk through what we mean by semi-formal proofs and where we have found them to be useful, like where they fit into our process. And then I'll walk you through kind of how we structure it, how we construct it, how we update it, revise it, and how some features of modern programming languages can really help us reason about and then enforce parts of the proof. More specifically, this is going to be about like sharing experiences and process. It's going to be compared to more traditional code reviews. So like as you can imagine, for some of my previous projects, there was very little tolerance for error, and the code reviews had to be like pretty stringent to make sure that we didn't like call the wrong winner of a national election. But I don't actually have a background in like formal methods. I have not surveyed them, and I'm not going to like walk through those. I think there might be some people here who actually do have a background in that. And if you do, like, I'd love to talk to you. Feel free to come up and like tell me all of the places that I'm wrong. As I said, I have teenagers. There's nothing you can say that will hurt me. This is not explicitly a like Antithesis is very cool talk, but Antithesis is very cool. Okay. So why don't we start out by just what are formal software verification methods as a point of reference. So this is an approach where you basically borrow the techniques from formal mathematical proofs and apply them within the context of software development. And there's a lot of very powerful tools for how you reason about and describe and map your code onto very specific symbols, and then there are very powerful solvers that can go through and analyze the structure of what you've done and determine whether or not your software actually does the thing that you claim/hope that it is actually going to do. Usually these are applied in slightly more constrained environments, so device drivers, cryptographic libraries, embedded systems, places where the set of inputs are kind of a little bit smaller, kind of the state space is a little bit smaller, and it's a little bit easier to reason about. And also places where the cost of failure is incredibly high, right? It's a security breach. It is a lack of availability where availability is crucial. It's like an aerospace crash problem, right? Lives are on the line. So that's a formal software method. So if formal software methods are kind of like over there, and you really, really have to cross your T's and dot your I's, and traditional code reviews are kind of here on the spectrum, where you kind of have to convince a skeptical coworker that you have actually done everything correctly and didn't screw it up. Semi-formal methods are kind of in the middle here. Like, we borrow some of the language and some of the structure of formal proofs, but we're not really going through all of the steps, and there's not really a set of tooling that spits out a, like, you got it right or wrong. If you're coming to the happy hour later, come catch me, and I will describe code review processes for private GitHub repos. Okay, so I'm sure many of you have heard of test-driven development. I want you to kind of think of our approach to semi-formal proofs as logic-driven development. You kind of lay out the argument for how you want things to be structured, and then once you've got that down, you start kind of layering the code onto that and try to determine whether or not the thing that you're doing actually does the thing that logic says it needs to do. So where have we found these kinds of approaches to be useful? So kind of somewhat similar to places where formal proofs are useful, where there's a constrained environment, the inputs and outputs are like that state space is a little bit smaller. Semi-formal proofs are useful in areas of your architecture that are serving as a boundary between like the outside world and the innards of your system. So if, for example, you've got like the public internet, and then you've got like your internal cloud, if there's one part of your system that has heightened responsibilities, that would be a good place to apply a semi-formal proof. Maybe not necessarily all of the like juicy innards on the far right-hand side there that an attacker would want to, because there's a lot of kind of cross-communication there. But these boundary layers, this can be particularly useful. So as a great capitalist once said, in essence, put all of your eggs in one basket and you really, really watch that basket, especially given how much eggs cost now. Okay, so drilling down to the next layer, what are the actual parts of our semi-formal proof? The first one are definitions, and this is kind of how you think about the world. These are the entities, the actors, how they relate to each other, what kind of communication there is, and this is putting words to them that you will use in all of the rest of the parts of your proof. This is your taxonomy. The next step are your assumptions. This is what you believe to be true about the world. And to be clear, like, some of this is going to be wrong. Like, some of it might be grossly wrong, some of it might be subtly wrong, but it is very important that you actually write down what you believe to be true. Because then, as you maybe start to believe things that are a little more accurate, a little less untrue, you can go back and you can examine the proof to see where you made those bad assumptions and where you might need to tighten things up or make some changes. Next, you've got requirements. These are your goals. This is what you're trying to do here. This is what you're trying to keep secret. This is where you're trying to preserve the integrity of certain parts of the system, kind of laying that out. And then finally, you have the obligations. Now, this is where the rubber really meets the road. This is, in the world that you assume to be true, and the thing that you've described and taxonomized, what must your code do in order to make sure that you achieve your goals? And obligations map directly onto the code. This is the parts of the code base where they must do something specific. Okay, so definitions, these, as I said, are like your taxonomy of the world. So if you've got a requirement, right, an authorized user can view a report, right? There's a few things here that you kind of need to define, right? Like, what is an authorized user? What does it mean to view a report? And a traditional architecture diagram might look something like this, right? You know, you've got your authorized user on the left there. Maybe they've got an SSO cookie that shows that they're authorized. They present it to the server. The server checks it out and is like, yes, this is an authorized user. It fetches the report and then shows it. However, if you kind of dig down a layer, the authorized user, you probably intend for that to be a human being, right? There's probably like an actual person somewhere that you want to be authorized in order to view the report. And actual human beings cannot really give cookies to computers. So what do you need to do? Let's revisit that definition again. An authorized user can view a report. So at the end of the day, you still have that actual like human being on one side, and you've got the report on the other. But there are some other parts that you have to taxonomize here, right? They probably have a computer. That computer is probably running a browser. That browser is probably the thing that actually is storing the cookie. And then the browser is running an origin, right? Interpreting the HTML, running the JavaScript, crafting the requests that are going to the server. And that origin is the thing that is actually sending requests into the server. The server is then going to evaluate that, determine if the request has the credentials to be authorized to view the report, and then send it back. Now, you could theoretically go even further and be like, well, this is running on an operating system which has a networking stack. It's really kind of your choice as to at what level of detail you taxonomize everything, but it's important that you actually create this taxonomy and write it down. Next, assumptions. This is what you believe to be true about the world, right? So in my previous example, there's an authorized user, they're trying to view a report. There are maybe attackers that are trying to view this report and see what's going on. So some things that you might believe about this attacker are that maybe they can't actually see the URLs that are going across the wire. And so therefore, it would be safe to put security load-bearing stuff in the query parameters. But maybe the user is actually behind a proxy, or somebody can actually see these URLs. So maybe that's not safe. You can then refine that assumption and be like, okay, well, maybe the attacker can't get the user to actually complete a single sign-on flow on their behalf, can't be a confused deputy, and that the cookies that the user gets back from this SSO flow are secure within the browser. Okay, great. You can make a different set of design assumptions and obligations based on that. If you're even more paranoid, you can say, okay, I'm moving to a model where there's client certificates on the user devices. And the private keys for these client certificates are backed in TPMs. So now you're assuming that the attacker can't actually exfiltrate the certificate that proves the user's identity, and they can't actually get the private key off of the computer, which is great. Although you do realize that you're basically assuming that the attacker cannot afford $5 wrench and then get attached to the user and just hit them until the user gives up the laptop. Next, requirements. Okay, so these are your goals. This is the an authorized user can view reports. This is what you're trying to accomplish. And then obligations are, what are the things specifically that different parts of the code, or even your entire code base, must do in order for you to achieve your goals. And in our case, the end product of all of this is a proof and its obligations that are living within the code base. A lot of our important code is written in Rust, and so a lot of our definitions, assumptions, obligations, et cetera, are laid out in Rust.comments. So that's kind of a convention that you'll see throughout some more of the slides. And so you'll have proof sections, and then those will reference obligations, and then specific parts of the code will have these obligations. So next level of detail, let's try and put this all together and walk through some examples. Thank you for giving a short talk. So man, I can just go on and on for a while about this. I am going to put a lot of text up on the screen, but don't worry, I'm not going to read off 500 words of dense text. I'm going to kind of walk you through the different parts of them and hopefully try and convey the message, and you can read in more detail kind of as I'm talking. Okay, so we've got 600 lines, so buckle in. We've got a few hours until we have to be over at the happy hour. I think we've got at least a few dozen lemons to go through. No. Man, tough crowd tonight. Okay, no, this is a more realistic skimmed down version of what it looks like. Okay, so we have definitions. We have users. We have human beings that are involved in the system. Some of them are good. Some of them are bad. We have software that's running on systems. We have these user agents. They're doing things. They could be doing things on behalf of good people or bad people. These systems are sending requests. So there's communication happening between different parts of the system. And within the browser, we hopefully have a permitted origin. That is something good that is actually trusted to communicate and receive information back from the server. So those are our definitions of the entities involved. We have some assumptions. Maybe we're assuming that browsers are generally going to be modern and respect RFCs and implement common security best practices, and other assumptions that kind of flow out of that involve which headers may or may not be set on the incoming requests, depending on the context and the situation. If you're using the warp crate in Rust to write your server, maybe you're assuming that warp is actually going to do the right thing in terms of surfacing the headers associated with a request. And maybe you're assuming that the user is not going to leak their single sign-on cookies, they're not going to post them anywhere, and they're not going to install any malicious extensions. So, assumptions with kind of varying degrees of validity. And why don't we start out with what we're going to call a general obligation. So this is something that we need to make sure that the entirety of our code base actually respects and enforces. And that is, no information is leaked between requests. So if I'm looking at information in the context of a single request, I can be certain that it is absolutely coming from that one request, and I'm not kind of confusing some weird global state from a different request. Okay, so I've got my definitions, my assumptions, and a general obligation. Okay, so we've got a proof sketch now. Got kind of the proof language up top and then an Englishy translation down at the bottom. So what we're trying to prove is that our server does not violate the confidentiality of the service. And there are a few different parts of this. The first one is the definition, and that is we assume it's okay to show confidential stuff to authorized users, right? The second one is we're asserting through that first general property that if we're looking at information about a request, it is only about that one request, that we haven't leaked any information. Okay, so we've got an authorized user who can view confidential content. We are dealing with only a single request. And now we're going to try and reason that everything within the context of this request checks out and is confidential. So the credentials check out. The user's actually presented a valid SSO cookie, and there are some obligations and some assumptions that are going to help kind of prove that this is actually the case. And we're also going to assume that everything about the request comes from a valid origin. So this is going to be some combination of what we're seeing on the request and some assumptions about how browsers will actually behave. And if we can tie all of that together, if we meet all of those criteria and we can obligate the right parts of the code, then we know that the request comes from a good place, it's got the right credentials, I must have gotten them honestly, and so therefore we can actually reply to that request. Although there actually is something missing here in that replying, right? We've not yet reasoned about the reply itself. We've looked at the information that's coming in, and is it trustworthy to come in, but we haven't actually gone through and made sure that the way that we're sending information back is actually going to preserve that confidentiality. So we need to add a little bit more here. That essentially says we're going to set the right headers, we're going to do the right thing, so when we send a request back, that stays confidential as well, that it stays within that origin, and that it's not possible for something that might, like an attacker might have been able to inject or induce this request to happen, but we're still going to respond in such a way that if the browser is actually doing kind of a reasonable thing, the attacker would never actually be able to see that response. So we've got our logic, we've got kind of the English language version of it, so now let's try and see how this works in a code sample. So this one piece of code here, this is a Rust function, that simply checks, is the request authentic? And we've got the obligation up top, which very specifically describes what we need this code to do. Remember, like, what must the code do in order for us to end up in the happy state? And in this particular case, this can only return true if certain conditions are met. And these conditions have to do with the origin header and whether or not it's present, the host header, whether or not it's present, and whether or not these are both good things. We potentially have a custom HTML header or a HTTP header that have come in, and that provides some more information. And then we've got the and then at the bottom that kind of like ties all of this together. And up at the top, we've got a just kind of like manual tag that's like, okay, this actually has been reviewed, and we've got the commit hash of when it actually was reviewed last. So we can say, okay, this code actually meets the obligation. And if we do go through, so let's say like some engineer comes in and they're like, yeah, you know, I'm looking at this and it's just kind of like irritating me because I like for strings in my functions to be alphabetical, and you're going O for origin, H for host, X for that header, like that's wrong. I'm going to go through and I'm going to edit this. So they go through, and the first thing they do is they manually flip this to say, okay, like I'm making a change, it hasn't been reviewed yet, and I'm going to go through and I'm going to like alphabetize everything. Okay, everything is great now. The problem is they introduced a bug. And that bug is that the host status and information goes to the origin variable and vice versa. And this is probably not good. This is something maybe that like a normal code review couldn't have caught. However, this is where typed languages, strongly typed languages like Rust, come in handy. We can leverage them. We can say, okay, we're actually going to create these two new data types, a host status and an origin status, and they're each going to wrap this Boolean value so we can get the information back. But now the origin checker returns an object of origin status, and the host checker returns an object of host status, and in the function down below that ties it all together, they're looking at the right thing. And so if the software engineer goes in and swaps these checks around without updating the actual code down below, the types are not going to check out. And I don't know if any of you have done any Rust programming, but if you screw up your types in Rust, the compiler will not be chill about it. You will notice. So this means that we can essentially make the Rust compiler our ally, right? And there's a lot of different things that strongly typed languages like Rust can do to help you out in this, right? You can use custom types not just for this type of checking, but also to ensure that like certain actions have been taken. You can use private members to restrict where objects are even constructed in the first place, and kind of scope that to crates, files, modules, functions. You can restrict how you can like pass objects around to ensure that other parts of the code can't forge them, that they actually, like if they have them, they must have come by them honestly. And you can even restrict which modules can invoke certain functions. And all of these put together are really cool tools to help you ensure that your obligations are met. And it leads to an interesting property where simply possessing an object of a certain type is proof that you've done some amount of work or validation. So for example, here, in this little example, we want to make sure that only a locksmith can open the door. So we've got our locksmith crate with a key defined in that, and we've made sure that that key is only constructible by a locksmith. We've got our vault object. We have an open door, or we have a vault mod, and we've got an open door struct. And that struct is only constructible within this module. And in order to invoke the open door function, in order to obtain an open door, you have to have a key. You don't do anything with the key, you just have to possess it. And so this means that unless you actually possess a key, i.e. you're a locksmith, you can't call this function and you can't get an open door. So therefore, we can make sure that certain objects are only obtainable when certain preconditions are met. So, in closing, there aren't any like real magic bullets on this. Like the cost benefit analysis of like where you're going to do this and how much effort you put into this is really, really key. But semi-formal proofs really do have some benefits, right? They force you to think more about the broader world in which your code is running and where your system is executing, who's going to be talking to it. And this can provide you with like more assurance than just traditional code reviews, which focus a little bit more on like, okay, is this code right? Do we believe that it's done the right thing, right? Like you're moving to that logic-driven programming. And this can result in code and systems that are a lot more reliable and secure. Now, the downside of this is this does require a lot more work. And by a lot more work, I do mean like integer multiplier amount of time to make, even like some small changes. So again, you like really have to figure out how you're going to commit to this and what you like to do. But the good news is, as I've demonstrated, strongly typed languages can really be your ally in here, right? Like the Rust compiler can be a real jerk to deal with at times, but like make it your like asshole ally essentially. Like make it so that if you screw something up, it will not go quietly, that you will get flagged. Now the nice thing is you can also play around with like one or other of these parts separately, right? Like you can try and start layering in some of the techniques around assumptions and definitions and logic reasoning about your system without necessarily like having to start writing code in Rust. Conversely, like if you're working in a strongly typed language but you don't necessarily want to like start writing a lemma, then you can absolutely start using some of these visibility and constructability techniques in order to improve the overall security and reliability of your system. So in short, you don't actually need to like upgrade your entire wardrobe like in one go. You can just like buy the blazer and then you can buy the slacks some other time. So thank you.
When you get the questions, could you repeat them?
Yeah. Yes.
What kind of tooling do you have? Like noticing when code has changed since the last review, or managing the graph of definitions and obligations?
So the question is essentially like, how sophisticated is the tooling to help us kind of keep track of all of these things? I think the short answer is we're also kind of like developing that as we go. I think I actually saw some code on a branch a few days ago that was like, we should actually ensure that like the blame layer and these obligation review tags like actually line up to some degree. So I think that's the third part that we're starting to put into place.
Cool.
Yeah. Yes.
So, can you give us a sense of what it looks like to put up a PR and antithesis? How do you review that?
So the question is like basically like what do PRs look like at antithesis, right? So when you're not dealing with the code that really is kind of at that boundary layer, like if it's not the web server, if it's not the API server, it's nearly identical to like code reviews in other places. It's really only when you're starting to work on these services that the process looks a little bit more like, okay, you start sketching out usually some combination of like new goals, new definitions, and maybe even kind of starting to like proof of concept the code a little bit, just with the understanding that that code is likely going to change. There are certain common software engineering patterns that actually kind of end up being bad or less desirable in this, like just a generic function that does something, right? Like, the open door function actually had like a bunch of layers and some hoops that you had to jump through. So anything that you prototype is going to end up looking very different. We've been working on adding like a new authentication system to our server. Well, I'll rewind a little bit. Like last summer we added support for SSO to view reports. That probably took about like 2 to 3 months of pretty rigorous discussion and proof work. Like the code itself was maybe about like a third or a quarter of the time, and the rest of it was really kind of going through, do we have the right argument? Does the logic check out? Is the argument itself internally consistent? And then, okay, let's look at the code. Does the code actually implement the correct thing? Does the code meet the obligations? Are the obligations sufficient to actually like make us, end up in this happy world where only authorized users can view reports, things like that. So for everything else, really straightforward for this boundary layer, for these services. It's a little bit more involved. Yes?
Yeah, from your experience, did you find that there are like certain classes and properties that are hard to actually enforce just with the type system alone?
Okay, so the question, as I understand it, is like, are there things that are really hard to do, like even with the type system, or is it like, are there things that the type system makes more difficult? The first one. I don't think we've really found stuff where the type system ends up being a limitation. We actually more recently started moving to a world where like each type actually kind of has like a lemma associated with it. So we can have like our Rust doc for a certain type will have the like 5 or 10 or 50, whatever, like how many lines of logic proof. But then like the top line statement, where it's like, authorized use, like if you have this type, then that means like X, has been incredibly handy in the top line proof. So I'd say that the typing system itself, from just like a programming language approach, hasn't been too problematic. And the way that we've actually started to wed that with some of our proof techniques has actually made things a little bit simpler in the long run. The back there.
Let me know if you can't hear me.
You're good.
I'm interested in how you kind of handle like shared definitions or even like referential definitions, right? Like presumably some kind of lemma or something that you prove in the authentication system.
Mm-hmm.
You can actually like use that as an assumption or as help for another proof later on. So like, do you just have kind of a text organization system around all this, or how?
Okay, so the question, as I understand it, is like maybe what's the boundary between like definitions and lemmas or things that we're able to prove, and organizationally, how do we track all of that and make sure that everything ends up consistent?
Yeah, more or less in like an informal comment system. How does that play out?
Okay, so it is a little bit challenging. We do a number of like passes over each change, obviously, and we will kind of like sit down and be like, okay, is this something that we're assuming to be true, or is this something that we can like prove to be true? And there definitely are cases where we've looked at something and said, okay, like we could maybe try and prove that this is true, but we don't have confidence that we've actually got the logic right, or that we like fully understand the security posture of what's possible both internally and externally. So we're actually just going to make this an assumption right now. Like we're going to assume a more spherical cow version of the world than actually exists at that point. And then, okay, like we'll go back later and we'll see if we can tighten up that assumption. We'll learn a little bit more. We'll see what changes we can make to, like what can we learn about what's possible, either from, what the rest of the world does, like what do browsers do? Like let's learn more about origins and contexts and cross-origin requests and see what we can do there. And this thing that currently is an assumption might be something that we can actually like end up proving and will end up as like the top line statement in a lemma. So there can be a little bit of fluidity there depending on the situation. I think I saw your hand go up first. Yes?
With advances in reasoning models,
Mm-hmm.
have you experimented with trying to get automated disproving of the proofs that you're writing to speed this up so you don't have to argue for as long with another human being?
So the question is, are we going to get computers to argue on our behalf instead of with actual people? Is that?
As a prefix.
Right. Like as a okay. So the more serious question was like, are we looking at using any sort of like automated reasoning tools to try and like lay out the earlier versions of the proof sketch, and then have a person kind of like come in and reason about the initial sketch that's already been laid out? Is that?
Or the inverse of you write a thing,
Okay.
and then you have O3 try to disprove it.
Okay.
Argue back and forth until you're pretty confident before you share it with another human being.
Okay, so the idea would be like we posit something and lay out an argument, and then have like an LLM or some other large AI system like try and poke holes in our argument. We have not tried that yet. I think my my most recent experience with using LLMs to try and program something was I was trying to, this is in the sports world, trying to say like, okay, I need to figure out if it's possible to take n variables from like a random distribution, but have them all like sum to 0 because it's a closed state, and write some Python code to do that. And I came back like 15 minutes later, and there was just like a wall of like dense mathematical equations and no Python. And then I was like, could you actually like write the Python script that does this? And it thought about it for like 200 milliseconds and spat out like 6 lines of Python, which were essentially like randomly draw n-1 random numbers, and then set the nth number to like the sum of those but negative. So it really was the internet. It's like math exchange. We're going to do 15 minutes of arguing, and then like your stack exchange where you get like 6 lines of Python code that might be right. So we've not really looked too much into using AI to be like a reasoning assistant or to be like a devil's advocate in a way. I mean, it's an interesting idea, but I'm not sure that it's really there yet. And the side effect of the approach that we're using right now is that you're also like training new people on kind of how this works. Now, to be clear, like I want to give a shout out to Dave Shearer and Brian Lagoda, who are our CTO and co-founder, and then the previous head of infrastructure. They were the ones that really like came up with this proof model, and I'm kind of the current steward of it. And so therefore, like the person who ends up arguing the most with Dave about it. But this approach also kind of helps new people coming into our infrastructure learn about the approach. And yeah, like there are some efficiencies that we could have with AI, but I think there's also value that we get out of like actual human beings being involved in this discussion. Yes.
It seemed like you were getting like pretty detailed in like the comments, the proofs.
Yeah.
And have you, like, if you're already going to that level of detail, have you looked at using some more automation-friendly, actual formal proof methods? Like, for example, there's liquid types now for Rust. A lot of the things that you were expressing, you could have get checked by an automated Turing prover there. Is that something that you've tried or are thinking about trying? Or?
So the question is basically like, since it seems that we're putting a lot of effort into like manually typing up a lot of this, are there any automated tools that we've looked into to kind of help the process, either from like structuring the argument or like checking the underlying logic in the argument? Is that the?
Yeah, kind of just like moving a little bit closer to like an automated check.
Sure. So the short answer is we haven't yet, but I think we are kind of starting to hit the point now where the system that uses this approach is getting large enough and has enough features that we are kind of hitting the part of that XKCD chart where it's like, yeah, maybe we should actually start automating this now. But yeah, like I said to I think Jesse's question there, we have only really just recently started looking at tools or like writing our own tools to like cross-check some of this. So if you have ideas, like come catch me later, because this is something where it's starting to become a bit of a like, yeah, we should automate parts of this.
For that matter, why have these be comments and not like assertions, which would possibly help you catch these when you're running like through tests, for example?
Sure. So the question is why comments and not assertions or some other method. The short answer is that assertions are definitely like really, really good at ensuring that certain requirements are met or that assumptions are met. But this is more about like ensuring that we're reasoning about the broader world correctly, right? So an assertion might be helpful in enforcing an obligation, but it probably is not going to be helpful in terms of the definitions, the assumptions, and then like the broader argument that we're actually like piecing this all together well. That said, we actually do, I don't know if there are any antithesis users or familiar, but we do have SDKs that we encourage our customers to use to write insertions that can be useful when we are testing their software to ensure that certain conditions either are never met or are occasionally met. Like, occasionally I want to make sure I get to the end of this long test. We do use those internally on this. We actually like throw all of our own system into itself and test it, which is a whole other story that I'm not the right person to talk about. But I think I see assertions as a complementary approach to this as opposed to something that's going to replace parts of it.
Your examples have been about security, and I wonder if you think that some aspects of correctness are better served by this approach than others?
So the question is that a lot of the examples were around security, and to what extent could this also be useful in correctness?
Other kinds of correctness.
Or yeah, other kinds of correctness.
Yeah.
Entirely possible, right? Like we're definitely coming from this from a certain point of view of using this in a place where we want to maintain the confidentiality and integrity of our internal systems, as opposed to the correctness of certain other parts of our test infrastructure. I think approaches like this could be definitely applicable and helpful in situations like that. We just haven't tried to use them there yet. I think maybe one more. Yeah. Yep.
Yeah, just as a person who's never seen a formal proof, can you give me a sense of like what makes this a semi-formal proof? If that makes sense.
Yeah. No. I mean, I mean, like kind of going back. Yeah, I think it's the fact that it's in a comment and we're not using one of the multiple like programming languages where you have to like really sketch out kind of the details of this either inside of or like as your code. Again, like I'm not as familiar, so somebody could certainly tell me that the answer that I just gave was like completely wrong.
You're relying on other humans to make sure the logic is sound.
Exactly.
In a shared language versus writing a formal proof that can be verified based on logic rules from
Right. It's human reasoning about things and then using like Rust types and certain things to automate parts of that, but not like going whole hog into the like, tuxedo and black tie. Okay. Thank you.